All right, we're going to take a look at another optimization problem here. So with this question here, we are told to find the points or point on the following function. So they give us a parabola that is closest to the point 0, 3 here. So I'm looking to find the points on our parabola here that are close to the point 0, 3. So let's go ahead and graph this parabola. First of all, just get an idea of what's going on here. So I've got a parabola opens downwards right on our y-axis. It's going to look something like this. And then you have the point 0, 3, maybe somewhere right about here, let's say. So I've got the point 0, 3. And I want to search all along this parabola and try to find all the points where the distance from my point 0, 3 to this point on the parabola is minimal. So the shortest distance that exists. So I obviously don't know what that point is yet, so I'm going to let that point be arbitrary. If my first coordinate is x, the next coordinate must have the relationship of being 6 minus x squared. So I'm looking to minimize essentially distance here. So when we're minimizing distance, I go to my distance formula. So the distance is going to be the square root of the change in my x. So this would be x minus 0 quantity squared. Again, that's x2 minus x1 quantity squared, and then y2 minus y1 squared. So my distance function, which is a function in just x, is the square root of x squared, plus this will simplify to become 3 minus x squared squared. So now I'm looking to find the derivative of this function, find its critical points, and then examine these to try to find minimal distance. So our next step here is to take our derivative. So taking the derivative of this will be d prime at x, is we're going to drop down the half and subtract 1. Derivative of the inside is going to be 2x, plus drop down that 2, and derivative of the inside. So therefore, d prime at x is going to equal 2x minus 4x times 3 minus x squared. I'm going to push that to the bottom. This would be 2 to the square root of x squared plus 3 minus x squared squared. So now I have my first derivative here, d prime at x. We can clean this up still, so I'm going to go ahead and distribute the minus 4x into the binomial here. If I do that, I'm going to get 2x minus 12x is going to be negative 10x, and then that'll be plus 4x cubed all over 2 times the square root of x squared plus 3 minus x squared squared. Okay, so now took our first derivative. I'm looking to find the critical points. So your critical points exist where the first derivative is 0 or undefined. So the first derivative is 0 when the top is 0 here, so therefore the question becomes is when is 4x cubed minus 10x equal to 0? Well, that'll be 0. I can factor out a 2x, and I'll be left with 2x squared minus 5 is 0. So solving this here, this is going to be 0 when x is 0, or plus or minus the square root of 5 halves. So I've got 3 critical points here. If I continue this, I also want to examine when the bottom is 0. Well, if you take a look at your bottom expression here, the bottom is not 0 ever, because for the bottom to be 0, you'll notice that x squared is greater than or equal to 0 at all times. So the smallest that this can be is going to be a 0. And likewise, this is always greater than or equal to 0. So if I let x be 0, this will be minimal, but then by letting x be 0 here, this will end up being 9. So again, this won't be 0. Continuing that idea, if I want to make this 0, I would have to let x be root 3, but then this would be 9. So this expression right here will never be 0, so you don't have any points where the first derivative is undefined. So these are my only critical values here. So I'm going to evaluate each of these into my original function, right? You go back to your distance formula right here and sub it in. So I want to evaluate this at d at 0, d at the square root of 5 halves, and d at negative the square root of 5 halves. So just for reference here, let's grab our d at x here. So taking a look here, and again, I want to sub numbers into this here. So if I let x be 0 here, right away you're going to see this is going to be the square root of 0 squared plus 3 squared is going to end up being 3. Distance will be 3 if x is 0. And you'll notice that that's just grabbing x being 0, so you're actually taking this point, and the distance from here to here is going to be 3. Now let's take a look at the square root of 5 over 2. If I sub that into here, this is going to be the square root of 5 halves when you square it, plus this will be 3 minus 5 halves squared, which will be the square root of 5 halves plus 1 half squared is going to end up equaling the square root of 5 halves plus a quarter, which ends up being the square root of 11 over 4, which is root 11 over 2. So I'm getting the distance here comes out to be root 11 over 2. And if you calculate that, the square root of 11 over 2 is actually approximately 1.66 in distance. So you can see it is smaller than this one. So this is already a possible minimal distance. If I examine this at negative, the root of 5 over 2, just because it's on a parabola and it's symmetric, you're going to end up getting the exact same value here as well. This will also be 1.66 as well. So it turns out that minimal distance occurs when x equals plus or minus 1.66. And that will yield minimal distance. So it turns out that minimal distance will occur when x is plus or minus the square root of 5 halves. And that is going to yield a distance of approximately 1.66 units. So minimal distance occurs on both sides of your parabola at plus or minus the root of 5 halves. So it's happening sort of on both sides here of your parabola, and you're getting your minimal distance. This is an example of using optimization in calculus to find the points on a particular curve that is close to another given point in this question. All right, thank you.